introduce you for a couple of minutes.
Okay.
I'll make fun of you, and then we can start.
That's fine. I'll make fun of you towards the end, too.
Careful that I still have authority on you for the next
I know.
hour and a half.
I'm well aware.
Right, so I think we can start. It's my pleasure to introduce the defense of Rick Zhang. As Joseph and Ross, he was one of the first students in my lab, so he was instrumental in setting up my lab. He was in particular the first security officer for my lab, and in this capacity, he had to deal with a number of crises. He has been doing very interesting work in the realm of self-driving car and transportation networks enabled by self-driving cars. He has received a number of awards, and he'll discuss about it at length. Rick has a fairly sophisticated taste in terms of food and wine, as you might have noticed, which made sometimes the social dinners quite expensive. But on the positive side, he has been providing the lab with interesting things, like, for example, a lamb specially cooked French style sous vide is the style.
Sous vide, yeah.
Sous vide is the style. So he handcrafted a machine in his own apartment together with his mates, and he has been cooking for hours lamb there. Very delicious, by the way. When Rick started in my lab, he asked me when a professor decides whether a student is ready for graduation. So what I told him, it's when the community decides that you are a deep expert in the topic of your PhD. It turns out that a couple of years ago, there was an article on Forbes highlighting his research, and the article was saying, Professor Pavone and his collaborators have been doing X and Y. A few months ago, there was another article on Forbes highlighting his research, saying Rick Zhang and his collaborators. And I said, okay, so Rick is ready to become a physicist. So now, the stage is yours.
Thank you, Professor Pavone, for that wonderful introduction. Good morning, everyone. Thank you so much for being here. Today, I'd like to talk to you about the past few years of work that I've been doing on models and large-scale coordination algorithms for autonomous mobility on demand. And autonomous mobility on demand is basically another word for a fleet of self-driving taxis. Now, I'd like to motivate my talk today by highlighting some key challenges that are facing urban transportation in the 21st century. And it all begins with the growing urban population, mostly in existing cities. By 2050, the urban population in the world will reach 6 billion. That's a lot of people. And why is this a challenge? Well, it's because as more and more people crowd into our existing mega cities, there's going to be less and less space for urban infrastructure, such as roads and parking lots and so forth. And this is important because we really need these roads and parking spaces, because as a society, we are completely obsessed with our cars, right? So of all trips in the US, 85% of all trips are taken using private automobiles, whereas the other 15% are things like public transit. And what do we do with our cars most of the time? In fact, 90% of the time, they're sitting in our garage, not doing anything, right? So clearly, this is unsustainable for the future, and these challenges, they compound to produce other dangerous effects such as heavy pollution and congestion in our cities. So perhaps luckily, in the past few years, we're starting to see a potential solution emerging. And the key to this potential solution is vehicle sharing. Now, let me just give a quick few examples of the types of vehicle sharing that's going on. We have bicycle sharing, which is now in over 50 countries in the world. Examples like one-way car sharing, things like Car2Go or Autolib in France. And also on-demand taxi services like Uber and Lyft. So if we look at even the past 5 years, the growth of vehicle sharing has virtually been exponential. And so this is a great trend, but often, if we want to operate these systems as efficiently as possible, there are several important operational challenges. Perhaps the foremost of all of these operational challenges is what's called the rebalancing problem. And this is simply the idea that the distribution of trip origins are different from the distribution of the trip destinations. Right? Simply, some places are more popular than others. And what will happen if nothing is done is that more vehicles will accumulate at some places in the city and be depleted at other places in the city. So the operators of these vehicle sharing systems will have to figure out some way to rebalance the system. Now, for bike sharing, what you would do is load up these bikes onto trucks and then rebalance the bikes through the trucks. And the problem here is to basically find routes for these trucks that are not only the shortest, but also is able to rebalance the most bikes. So this is quite an interesting problem. For one-way car sharing, obviously you can't put these cars on a truck, so it gets a little bit more difficult. So often what people have to do is you have to hire drivers to rebalance these vehicles for you. And then the problem becomes, well, now these drivers become unbalanced, so it adds another dimension of difficulty to the problem. And that's very interesting as well. Finally, for taxi systems, the problem is arguably not as severe. But for the efficient operation of the system, it's important for cars to know where they should go when they don't have a customer in the vehicle. Right? Where should the cars go to look for the next customer? And for taxis, ultimately the driver has the final say on where they want to go. And this location may not always be the optimal location for the system as a whole. The research and the models and algorithms that I'll be presenting today can be equally applied to car sharing systems as well as taxi systems. But what I like to focus on instead is another new emerging mode of transportation. And that is the idea of using autonomous vehicles to transport customers through an urban environment, and essentially combining autonomous vehicle technology with car sharing to create what we call autonomous mobility on demand. Now, there are several key benefits of autonomous vehicles. The one that's highlighted the most often is safety, right? So as the technology matures, the autonomous vehicles have the potential to dramatically decrease the amount of traffic fatalities in the world. But what I'm interested in this talk, what we're interested in today, is that autonomous vehicles have the potential for system-wide coordination. And what this means is that because they're autonomous, there's no driver on board. So if we as the fleet operator tell the vehicle where to go, then we can be sure that they'll do exactly as we say. And this we can potentially increase the efficiency of the system overall. So how do we control a fleet of autonomous vehicles? Well, what does that even mean? As with any control system, there are three key elements. The first key element is the model of the system. In our case, this means the travel demand in the system, in the city, the road network of the city, and potentially vehicle states, such as the level of batteries, if they're electric vehicles, and so on. We have control inputs, which is the decisions that we made to control the system. And these involve the routes for the vehicles, computing routes for both passenger vehicles and for rebalancing vehicles. And also vehicle-to-customer assignments, right? Which vehicles should we assign to which customers? We can measure the performance of our control system using several performance metrics, and these are usually measures of quality of service, right? So how long is the customer waiting time, right? What is the vehicle availability? Things like this. And now, since autonomous mobility on demand doesn't really exist anywhere in the world yet, there are still lots of things that we don't know about them. And so I've put together a list of key questions that I would like to ask, and also tell you about ways that we will go about addressing these questions. Now, the first question came up with is, let's say we want to have an autonomous mobility on demand in a city. How many vehicles do we need, right? How do we design such a system? given those vehicles, how do we route the vehicles optimally, both the passenger vehicles and the rebalancing vehicles, to ensure quality of service, and also be scalable so that we can scale this to a city-wide scale that's potentially hundreds of thousands of vehicles, right? So these are very big systems. How do we assess the societal benefits of these autonomous mobility on demand systems, or potentially drawbacks, right? We don't really know. And finally, what I'll discuss is that what effect does autonomous mobility on demand have on the level of traffic congestion in the city? Will it increase congestion to the point that it completely paralyzes the city road network? We'll talk about that in a short while. And before I go into answering all these questions, I'd like to look at some of the previous work that has been done that's related to this field. And we start with the transportation community, which has been studying traffic for the better part of the last 50 years. And one of the most relevant techniques in the transportation community is what's known as dynamic traffic assignment. And what this approach essentially is that we are given a set of origins and destinations, and then we try to route the vehicles on a road network to go from the origins to the destinations, and compute the travel costs in an iterative manner until we reach some kind of equilibrium. Now, what does this mean? An equilibrium is when any one vehicle, if it chooses to switch to another route rather than the one it was assigned, then inevitably its travel time will increase, right? So we reach an equilibrium where everyone cannot decrease their travel time by switching routes. Unfortunately, the problem with this technique is that it doesn't address some of the key operational constraints that are associated with autonomous mobility on demand, namely, it can't take into account things like rebalancing. In fact, in most of the traffic transportation literature, the goal is often to analyze the behavior of traffic rather than to explicitly control traffic. And the works that do work on control of traffic are often limited to things like the control of intersections and highway on-ramps and things like that. So the study of control for autonomous mobility on demand has evolved rather from the operations research community and the robotics community. And so along this vein, one of the first works that address the problem of explicitly controlling autonomous mobility on demand is actually done by Professor Pavoni, where they assume that the vehicles and the customers are a continuous fluid that move through a transportation network. And this approach was great. It was able to offer a lot of insights into the behavior of the system, but unfortunately, it doesn't account for the stochastic nature of the system. Right? Customers in real life are discrete, and they don't arrive as a fluid. They arrive according to some random process. So we would really like to take into account this stochastic nature. Another related approach is called dynamic vehicle routing, and as it applies to autonomous mobility on demand, it's known as the dynamic pickup and delivery problem. And the idea is essentially we have a fleet of vehicles and a set of transportation requests, and we want to compute routes for the vehicles to service those requests. And while we're doing that, new requests can pop up in some Euclidean space. And actually, one of the great achievements for this approach is that we can actually model the entire system as one huge distributed queue. And we can formulate routing algorithms that are optimal in certain regimes. Unfortunately, these regimes tend to be regimes where the system is either under very light load, meaning that there's essentially no customers in the system, so it becomes very easy, or extreme heavy load, which means that the system is on the verge of collapse because there's too many customers coming in. Now, most systems operate somewhere in between, so for these regimes, it's harder, or these approaches cannot assess the quality of service for these systems. So that brings us to my contributions in my PhD, and it consists of 2 parts. In the first part, I develop queuing network models which take into account the stochastic nature of customer arrivals And also, we're able to develop performance metrics to measure the quality of service for the system. And indeed, we develop a systematic approach to, at the same time, design, analyze, control, and evaluate the performance of autonomous mobility on-demand systems. We then extend this for autonomous mobility on-demand to regular mobility on-demand systems with like car-sharing services with human rebalancing. In the second part of my contributions, we consider additional constraints, additional operational and structural constraints that are associated with these systems. An example of a structural constraint is the structure of the underlying road network, right, and how that relates to what impact congestion will, autonomous mobility on demand will have on congestion. Right? So for different cities with different structure of road networks, we can have different impacts. An example of an operational constraint is if we have an electric vehicle fleet, then they have limited range and they have to charge, right? So we take into account charging constraints. And here we actually develop a model predictive control framework in which we are able to route the vehicles in the presence of these operational constraints, such as vehicle charging constraints. So these contributions have been published in a number of journals and conferences, including International Journal of Robotics Research, IJRR. Conferences include RSS, ACC, CDC, ICRA, and so forth. So in the interest of time, today I will only go through the first and the third contribution. And this is mainly because the first one is the general model of the general queuing model for autonomous mobility on demand. And the second one is a little bit redundant because it can be viewed as an extension. And finally, we don't discuss autonomous mobility on demand with charging constraints because it's an MPC approach, model predictive control. And throughout the rest of the presentation, we use similar techniques to address the problem of rebalancing. So I will instead discuss the queuing network and what happens to these systems in congested transportation networks. So let's have a look at where we are right now. So next I will go into the queuing model. Oops, the queuing network model. So the model is as follows. We have a city. In a city, we have n stations, geographically distributed. And customers arrive at each station. And if they see a vehicle at the station, then the vehicle takes the customer to the customer's destination. If a customer arrives at a station and does not see a vehicle, then the customer leaves the system immediately. Now we call this a passenger loss model. And it's suitable for modeling impatient customers and also systems where we expect a very high quality of service. Now, from a technical standpoint, this assumption allows us to decouple the customer process, the customer arrival process, from the vehicle routing process. So we'll see how it allows us to formulate this, what's called Jackson network model. So in terms of the stochastic behaviors of the system, we assume that customer arrive at each station with some Poisson process with rate lambda. They are routed to other stations through a routing distribution that's static, that's called Pij. And the time that the customer spends traveling is an exponentially distributed variable called Tij. And now this exponentially distributed variable might sound a little strange, but from an analysis point of view, we'll see that it's very useful, and it allows us to to formulate the system as a Jackson network. So what is a Jackson network, right? How do we formulate the system as a Jackson network? A Jackson network is a queuing network whereby agents move through the queues in a system using a static probability distribution. At a high level, it's a Markov process. And it's been very successfully used in communication networks back in the early ages of the internet when they were trying to figure out routing data traffic. And so what we like to do is apply these tools that's been developed to this transportation network. And the key insight here is to interpret the stations as single server queues and the roads as infinite server queues. What do I mean by infinite server queues? Well, it's basically a queue where no matter how many vehicles you have in the queue, the travel time is unaffected. So in this case, we're not modeling congestion. That comes later. So with that, we have modeled a Jackson network, and it allows us to have to use all the tools of Jackson networks. So to clarify, what happens is that at one of these single server queues, vehicles form a queue essentially at the station, and they wait for a certain amount of time for customers to arrive. And the amount of time that they wait is exactly the inter-arrival time of the customers. So when a customer shows up at a station, it essentially services a vehicle, right? Takes the vehicle and moves on to the infinite server queue that represents the road. So the Jackson network allows us, as I said, to use some tools. So we can define some things. First of all, something called the relative throughput. And this is essentially the rate at which vehicles are moving through the queues. And the relative throughputs can be solved using these balance equations. And once we solve these balance equations, we can essentially solve for the entire probability distribution of the network. What does that mean? It means that for each station, we can solve the probability of having a certain number of vehicles at that station. Are we going to do that? Do we need it? Not really, but it's there for us, and it's analytic to compute. This factor G of M is a normalization constant, and M is the number of vehicles we have in the system.
A quick question.
Yes.
In your model, you have queues of cars at stations. Is that really
Correct.
just a conceptual tool? Do you actually imagine that represents cars driving?
Yeah, that's a very good point. Yeah, so for car sharing systems, it might be a real thing. For autonomous mobility on demand, where a vehicle can just come and pick you up, then it's more conceptual. So we can view these stations as regions in space where perhaps cars are loitering around or parked somewhere, and if there's a customer arrival within that space, then the car comes and picks the person up. So we can essentially incorporate that into the same model. All right. So we can define something called the relative utilization, which is a measure of how much each station is being used, and it's the fraction between the relative throughput divided by the customer arrival rates. And with a little bit of math, we can define a performance metric that we're really interested in, which is called the vehicle availability. And this is the probability that a customer will show up at a station and see a vehicle waiting for him, right? So this is the vehicle availability. Now, it's a direct function of the relative utilization and some function of these normalization constants of the probability distribution. Now, the availability can be computed using this formula, but alternatively, computing these normalization factors can be a little bit cumbersome. So we use an alternative method called mean value analysis, which is very efficient computationally, but I won't go through the details in this talk. So just to be very clear, this animation shows what happens at a station, right? Vehicles form a queue at a station, and when a customer comes, it takes the vehicle to its next destination, like so. And so in this case, we're saying the arrival rate of customers is also the service rate for the vehicles. And of course, when there's no vehicles, the customer leaves. It's the passenger loss assumption. Later, we'll see when we will relax this assumption and see what happens in real life. So up till now, I have not really said anything about rebalancing, right? The problem is, how do we incorporate rebalancing into this model while maintaining and staying within this Jackson network framework? So the key idea is this. We consider a specific class of stochastic rebalancing policies, whereby we generate these virtual passengers with some rate psi and route them. So when we generate these virtual passengers, if there's a vehicle at the station where it's generated, then the vehicle takes the virtual passenger to its destination, routed according to routing probabilities alpha. And if there's no vehicles at the station, then the virtual passengers also leave, just like the real customers. Now, because these passengers are virtual, when the vehicles are taking them to their destination, the vehicle is actually traveling by itself empty. So that encapsulates rebalancing. And so now the objective is to, what we want to do is manipulate these virtual customer arrival rates and routing distributions to minimize the number of rebalancing vehicles on the road, because that, contributes directly to fuel costs. And we want to be subject to the constraint that the availabilities at all the stations are equal. And so that's encapsulated by this gamma I equals gamma j. And if you recall, a couple of slides ago, we put up a formula for the availability, and it's directly proportional to the availability, gamma, sorry. So having gamma I equals gamma j implies that the availabilities at each station won't be the same. So this is the problem that we want to solve. And if we look carefully at this problem, first we notice that it's nonlinear, right? So in the objective function, we have a product of two optimization variables. And also this constraint is also nonlinear. So now we can apply a trick and introduce a new variable. Let's call it beta ij. And this variable essentially is collapsing alpha and psi into a single variable. And if we do a little bit of math on this constraint, we can turn it into this constraint over here, which is linear. And so we have turned the nonlinear optimization problem into a linear optimization problem, or linear program, which is very scalable to high dimensions. And so we can solve this for very large systems, potentially hundreds of thousands of vehicles. So let's have a look at what happens when we rebalance versus when we don't rebalance. So here on the x-axis, we have the number of vehicles. On the y-axis, we have the availability, the probability that you'll arrive at a station and see a vehicle waiting for you. And each one of these curves represents a single station. So in this graph, there's about 20 stations. And this is the case with no rebalancing. And what we see is that for most of these stations, right, no matter how many vehicles you have, the availability is bounded away from 1. So this might seem a little surprising, but it means that no matter how many vehicles you have, no matter how big your fleet is, if you don't do rebalancing, then there's always going to be some customers that you're not satisfying. Right? And so let's see what happens when we apply this policy and create a balance system. And now all of the curves for all the stations collapse into a single curve, so that as the number of vehicles increase, the availabilities at all stations approach 1 as desired. So this is great, right? Can we use it in real life? Right? Can we just apply it? Well, not really. There's a couple problems. The first one is that this is an open loop policy, right? Which means that we're just sending rebalancing vehicles from one station to another without taking into account the current state of the system. Right? And in practice, this probably won't work very well. And secondly, we have assumed the passenger loss assumption. So when a passenger doesn't see a vehicle, they leave. In real life, what customers might do is just wait a little bit, right, to see the next vehicle becoming available. So taking inspiration from this open loop policy, we can reformulate a closed loop policy that looks very similar, right? It looks very similar. Where now this NV is the number of vehicles, rebalancing vehicles we want to send from station I to station J. And again, we want to minimize all of these vehicles. But now what we're able to do is take into account the current state of the system, such as the number of vehicles at each station and the number of customers that are waiting. But there's a slight problem, right? Because MV is the number of vehicles that are rebalancing. So it's by definition an integer value, right? We can't send half a vehicle. So this is an integer program. And in general, integer programs are not very scalable to high dimensional systems. But it turns out that for the structure of this constraint specifically is what we call totally unimodular. And what that means is that we can relax this integer assumption and pretend that NV can take on continuous values and solve a linear optimization problem. And our optimal solution will indeed be integers. So this is awesome, right? So this means that we can scale this closed loop rebalancing policy to very large systems of potentially citywide scales. So we have developed an open loop rebalancing policy and then a closed loop real-time rebalancing policy. In practice, what we do is every few minutes, we solve this in a model predictive or receding horizon control fashion. Every few minutes, we calculate the number of rebalancing vehicles and we send them. So let's, yes?
What's the VE and VD?
Yes, so this is the number of excess vehicles at a station, right? So how many vehicles left over. And VD is how many vehicles we want to have at that station. Right, so this could be like a control, like something that we can design, right? We can set these numbers to even, or we can set them according to how used the station is. So let's see how these algorithms perform, shall we? And we do this by using case studies with real data. And here I will present 2 case studies. The first one we did for New York City, and in fact Manhattan. And what we did was we had access to taxi data from Manhattan. And the taxi data consists of, for each trip, an origin location, a destination, and a timestamp. So with that, we can estimate the parameters of the Jackson network, namely lambda, the customer arrival rate, the routing probabilities, Pij, and the travel times. And when we estimated all those parameters, we can do a similar queuing analysis as we did a couple slides ago. And in particular, we did this for 3 time periods. The peak demand, which is morning rush hour, average is like middle of the afternoon and middle of the night. And what we notice is that if we have 8,000 vehicles, right, the availability of the vehicles at peak demand is on the order of 90%. And so this is pretty good quality of service, right, 90%. And what this could be implying is that we only need 8,000 vehicles in Manhattan to service all of the taxi demand. To put this in perspective, there is actually over 11,000 taxis operating just within Manhattan. There's 13,000 overall. Over 85% of the trips are within Manhattan. And so this suggests that, we only need 70% the size of the fleet to be able to satisfy the demand. Could this be right? To further validate this result, we perform a simulation study, or we individually simulate each vehicle as it services customers. And in the simulation study, we use the real-time closed-loop rebalancing policy that I just described, and we have also customers waiting, so customers are not lost when a vehicle is not available. And in this case, the performance metric that we're looking for is the average customer wait time. And we see here with 8,000 vehicles, we're on the wait time of around 2 minutes, which is pretty good, I think. So this confirms the queuing analysis. And just to show you what the simulation looks like, here's a short video. And the green bars here represent the free vehicles. The red bars represent customers that are waiting. The cyan dots are vehicles with customers, and the dark blue dots are rebalancing vehicles. So we see that there's like waves of rebalancing vehicles that are moving from the outskirts of the city into the center where all the demand is. And so I must say that you see like vehicles moving through the park and stuff. This is because we're not using a road network of Manhattan. We're just simulating kind of point-to-point travel. They are using Manhattan distance though, so. At least that clears it up, makes it a little bit better. All right. So the second case study that we performed was for Singapore. And for this case study, we used 3 complementary sets of data. First is the Household Interview Travel Survey, or HITS. And the second is taxi data, and finally the Singapore Road Network. And this is more of a thought experiment. So this is saying, what would happen if we replace not just the taxis, but all forms of transportation in Singapore with a single autonomous mobility on demand, right? So all forms, that means all private vehicles, buses, metros, everything. And how many vehicles will we need? So here I'm only showing the simulation results, but it looks like with around 300,000 vehicles, you can get decent quality of service. Now, to put this in perspective, there is around 800,000 passenger vehicles in Singapore. So this suggests kind of a replacement ratio of at a minimum 3. Now, I'm saying minimum because we're also servicing all the public transit stuff, right? So we can replace at least 3 vehicles to 1. Using this result, we did a financial analysis for comparing autonomous mobility on demand versus a traditional private vehicle ownership model. And so that's what this is. So first we look at the cost of service. So for the traditional model, this is things like the cost of the vehicle, maintenance, fuel, things like that. And then we look at the cost of time, which is the time that you're wasting while you're driving in your own vehicle, right? So, and this is kind of priced according to the Department of Labor, some statistics on the median wage of the city. And we can add them up to get the total mobility cost. And what we see is that for autonomous mobility on demand, the total mobility cost is basically reduced by half, right? So even though this is more of a thought experiment, it illustrates the potential for these autonomous mobility on demand systems to not only provide quality of service, but also to reduce cost for the end users. So let's do a quick recap of what we just seen. Here are the key questions that I put up earlier. And what we have done so far is address questions 1, 2, and 3. Right? So we developed a queuing network model for autonomous mobility on demand that takes into account the quality of service metric in terms of vehicle availability. And we can size the fleet of how many vehicles we need in the city. We developed both an open loop and a closed loop control rebalancing policy. And we demonstrated this using case studies of both New York and Singapore. So for the last part of my talk, I would like to think about what impact does autonomous mobility on demand have on the traffic congestion in the city. Now, if we think about this really closely, why would autonomous mobility on demand increase congestion? Okay, so there's actually a big debate in the autonomous vehicle community of whether these systems will just completely paralyze the road infrastructure of the city, and the debate is not settled. Perhaps until now, we'll see. And if we think about why it might increase congestion, it's pretty easy. So assume we have the same number of passenger trips, right? Everyone still has to get to where they want to go. So you have the same number of passenger carrying vehicles on the road. But with an autonomous mobility on demand, what you have is these extra empty vehicles that are rebalancing. So in fact, you're adding more vehicles onto the road, or some people like to use the term vehicles miles traveled. You'll have more vehicles miles traveled on the road. And so this makes sense, right? More vehicles equals to more congestion, seems logical. But what perhaps this is not taking into account is the fact that we as a system operator have full control over these vehicles. So we have the ability to route these rebalancing vehicles perhaps along less traveled routes and not increase congestion so much in the city. So following this train of thought, we first perform a simple numerical study using a simple 9-station system on a really simple road network. We generate some random demands and route them uniformly on the road network. And then these colors are showing the road utilization of each road segment, or you could look at it as congestion. So then what we did was add rebalancing to the system by computing that open loop rebalancing policy that I talked about in the first part. And then we see that indeed there's going to be more vehicles on the road, right? So like some of these road segments are becoming more red. So we do this 500 times and we plot it here. And what this graph is showing is on the x-axis, the fraction of vehicle increase due to rebalancing. And on the y-axis, we're showing the amount of increase in road utilization or congestion. And we see that the mean utilization is essentially a linear function of the number of vehicles, because more vehicles on the road. But what's really interesting to note is that the max utilization, that's the road segment that is the most congested, right? So in this case, it's this red segment right here, right? So that road segment, in almost all cases, its congestion level does not increase with the introduction of rebalancing vehicles. Now, what is the intuition here? Anyone? Well, basically, right, the intuition is that rebalancing vehicles tend to move in the opposite direction of normal traffic, right? So intuitively, it makes sense. So next, we want to formalize this intuition, and we do so by using a network flow model of the system. So we model a road network using a directed graph where nodes in the network are intersections and their edges are road segments. Now the trips in this model are origin and destination pairs. And the congestion model that we're using is very simple. It's just putting a road capacity on each road segment. And to rebalance the vehicles, what we want to do is have the rebalancing vehicles route from the destinations of the trips back to the origins. They don't have to be the same vehicle, but you have to have all the destinations routed back to all the origins. I want to point out that this is a steady state analysis, and there's some limitations, which I'll discuss a little bit later on. And the key result that we're able to come up with using this model is this. Given two things. First, we want to have a set of feasible customer flows. What does this mean? It means that once we populate all of the flows of all the customer trips onto the road network, then all of the flows on any particular road segment is within the congestion or road capacity of that road, right? So the customer trips itself is not causing excessive congestion. The second key that we need is to have a capacity symmetric network. What this means is that for every node, for every intersection, the capacity of the road going into the node is equal to the capacity of the node coming out of it. Right, so you might think, well, is this the same as having each road having the same number of lanes in both directions? Well, no, actually, it doesn't have to be. In fact, this can take into account one-way streets. And as we'll see a little bit later for New York, where essentially every street is a one-way street. So it turns out that this capacity symmetric assumption is not such a limiting assumption. And we're actually able to, we did a quick study on major US cities and found to a large extent the road networks in these cities are capacity symmetric. So if we're given these two things, then we can always find a feasible rebalancing flow. That means that implies that in this model, rebalancing does not lead to increased congestion. Right. So this is great. Sigh of relief a little bit. We're not going to paralyze the road networks. However, so before I discuss the limitations of this model, let me just give you a quick intuition on how this proof works. So let's say, and we do this by contradiction. Let's say that we absolutely cannot find a feasible rebalancing flow. It doesn't exist. But what we can do is try our best, right? We can try to rebalance as many vehicles as possible. So here what we're trying to do is rebalance these blue squares into the circles. And so let's try to find some routes. Oh, we found one. So that's great. We're able to rebalance that pair. So let's take it out. But what happens now is that this road segment becomes saturated. Right? Its usage is equal to the capacity of the road. And in fact, what will happen is that the saturated road segments will form a cut in the road network. It will separate the road network into two pieces, where the origin that we want is on one side and the destination is on the other side. And it turns out that if we can't find a rebalancing flow, then this will always happen. And also, the only way this will happen is if the capacity of the road going into one side of the network is different from the capacity of the road coming out of it. Right? And essentially, this means that we have reach the contradiction of the second statement that we need a capacity symmetric network. So as I said before, this was a steady state model, and there are some limitations. In fact, in real life, we could have unexpected fluctuations in the traffic of the city. So we might send a rebalancing vehicle only to realize that it's later going to cause congestion. So what we want to do is formulate a rebalancing policy that takes into account this congestion, that knows about the congestion levels in the city. And the key idea here is, if we know that we're going to send a rebalancing vehicle and it's going to increase congestion, let's just wait a little bit. Let's not send it right away, right? And so this is what we formulated. And it's actually very similar to the optimization problems I showed before. Here we have essentially the same objective of minimizing the number of rebalancing vehicles on the road. But what we added here is some slack variables that say that if this rebalancing is going to lead to increased congestion, that means violating these congestion constraints, then we put those vehicles into the slack variables and we say, let's not rebalance them. And so if we have a look at this optimization program, we notice that this is also an integer program. The number of rebalancing vehicles is an integer value. But it turns out that this problem also has a form that its constraint matrix, this one, is totally unimodular. So it means that we can also solve this problem as a linear program, and the results, the optimal solution, will be integers. In fact, this is one instance of a well-known problem called minimum cost flow. And so by now you're probably wondering, hey, this guy's just lying to us. Probably all of these problems are, integral. But we tried very hard to make sure this is actually true. So this is great because this allows us to scale up this algorithm to very large cities as well. So let's see how it performs. We do a similar study on Manhattan using a Manhattan road network. And what we're doing here is, for the passenger routes, we are computing the routes for each passenger vehicle using a well-known graph search algorithm called A-star independently. And then once in a while, we are solving that optimization problem and then sending out the rebalancing vehicles. And we compare our new congestion-aware rebalancing algorithm with a baseline rebalancing algorithm, which is actually the first algorithm that I showed you in the first part of the presentation, which doesn't know anything about congestion, right? So just keep sending rebalancing vehicles no matter what. And let's see if this can play. Yes. So as more and more vehicles populate the road network, we're starting to see congestion regions forming up in this baseline rebalancing case. And for the congestion-aware case, we're seeing that it's recognizing that there's going to be congestion, so it doesn't send as many vehicles. And in fact, it maintains the level of congestion in the road network to a reasonable level. Right. So let's have a look at the numbers. And indeed, the congestion-aware algorithm is able to service more trips, have a smaller wait time, as well as a smaller travel time because there's less congestion on the road. And we note that we also sent far fewer rebalancing vehicles. Now, there's a couple takeaways from this. And the first is that if we don't do anything about congestion, if our system is not congestion aware, then absolutely it can increase congestion in the city. However, if we do rebalancing in an intelligent way by taking into account these congestion constraints, then we can avoid that. And second, you might be asking yourself, well, surely some of these rebalancing vehicles that are being held up, they got to go somewhere, right? Well, doesn't that affect the quality of service at the other end? Well, certainly it's a valid concern, and there is a trade-off here. But here what we're able to show is that you can get away with reducing the number of rebalancing vehicles and still maintaining quality of service. It's an interesting problem for the future to investigate what is the minimum number of rebalancing vehicles you need to actually satisfy these customers. And so in conclusion, I'd like to just go back to our key questions and In the first part of the presentation, I showed you a queue network model of autonomous mobility on demand, and we developed a systematic approach to design, analyze, control, and evaluate the performance of a mobility on demand system through case studies of Manhattan and Singapore. And in the second half of the presentation, we discussed what impact congestion will have, what impact autonomous mobility on demand will have on congestion. And the answer is, if we do rebalancing in an intelligent manner, then it has the potential of not increasing congestion in a city. Now, this field is only in its infancy, and there's actually much more work to be done. What's really interesting is that there are some university groups that are now applying this queuing network model to analyze and study even cooler systems, like how do you prevent cyber attacks in these systems, and it's pretty awesome. So I only listed a few future research here, and the first is that we would like to extend the queuing network model to a model with congestion constraints. And I have some ideas on that if we can talk about that later. The second one is we want to see how we can reduce congestion in the city even further by using ride sharing or carpooling, or just staggering the demand, right? Letting the customers maybe wait for 5 minutes and then travel in a less congested road network. Third, we want to integrate public transit, existing public transit infrastructure with autonomous mobility on demand to solve what's called the first mile, last mile problem. And number 4, we want to explore decentralized architectures. So everything that I presented today was what's called a centralized architecture. We have a central operator that's making all the decisions. And the great thing about decentralized architectures is that it's more robust to failures. So it'd be interesting to investigate the performance of algorithms under this architecture. And finally, we want to demonstrate these algorithms on real self-driving vehicles, providing a mobility on-demand service in some community. And I conclude with a vision for the future. This is from the 1950s, showing autonomous vehicles in the future. And over here, we have another very similar vision from not too long ago that will hopefully become a reality in the next 5 years. And so first and foremost, I'd like to thank my committee. Professor Marco Pavone, my advisor, you taught me so much. You taught me how to do research properly, how to proceed with diligence and handle everything in the style as a perfectionist that you are. And I'm very grateful for that. Professor Steve Rock, in my first 2 years as a grad student, you were my mentor, and you continued to support me even when I left to join Marco. And I can't thank you enough for this. Professor Max Schwager, welcome to Stanford. We actually met back in 2013 at the University of Waterloo, where we had a number of interesting discussions on mobility on demand, and in fact those discussions led to some of the work that I'm presenting today, so thank you very much for your contributions. Professor Michael Kokendorfer, he taught me many of the techniques of decision making that I've used extensively in my research, so thank you for doing that. And finally, it's an honor to have Professor Ilya Sterbolev as my chair. Ilya joins us from the GSB, and he's actually the faculty advisor for the Stanford Wine Society and was indirectly responsible for getting me addicted to Madeira. So thank you. I'd like to thank the Dr. Cleve B. Moeller Stanford Graduate Fellowship and the NSF for providing funding for my research. And also, I'd like to thank the AeroAstro staff, Patrick, Robin, and Jenny, for always being very helpful with anything that I need. I'd like to acknowledge my friends at Stanford. A particular shout out to Federico Rossi, who I collaborated with on numerous occasions. It was very great working with you. And he's also responsible for putting together this wonderful live stream system that we have. Another special shout out to Edward Mazenk, who provided the delicious food that you'd enjoyed today. We had some very good times. And to my friends in the ASL and the ARL and in the Aeroastro department. It's been really fun. And I like to point out that this is Marco. This is Professor Pavoni. Believe it or not, he used to be a good skier.
Wait for a few months.
And finally, I'd like to thank my parents. 18 years ago, my parents gave up their jobs, gave up their way of life, and moved to a country where they had no jobs, no money, no friends, and didn't even speak the language. And they did it all so that I would have my best shot at life and at a great education. And 18 years later, here I am today talking to all of you. So I can't express in words the gratitude that I feel for you supporting me through all of these years and just being with me every step of the way. I guess I would like to end with I love you and thank you. Yes.
Can you tell me like the main difference between the mean availability analysis on the Jackson network model and the continuous model of the fluid flow from before? Like you mentioned that was a problem previously.
Yeah. So the mean difference the key difference between the fluid model and the Jackson network model is that with the Jackson network we are able to take into account the stochastic arrivals of the customers, and we're able to compute performance metrics, right? The vehicle availability, which is not given in the fluid model. And in fact, we can compute more than that. We can compute, in fact, the entire probability distributions of the entire system, and we can compute, second moments of the entire distribution of how the vehicle availability and other metrics that we're interested in, right? Queue lengths, everything. So I didn't exploit the Jackson network model to its full extent. I believe there's people currently working on that actually, but it's something that we can do. Pepper?
When you did your simulation of the original model with congestion, was it aware of adjusted jump times?
Yes. Oh, wait.
Because it would take longer to get from one station to another or from one place to another. Was the model aware of that, or was it doing it based on distance, or?
So yeah, it was aware of that, and like it will send. What will happen is that it will just try to send different vehicles from other places, right? And because the routes are not computed by the optimization algorithm, the routes are simply computed based on A star actually. Then these vehicles don't know to take the less congested routes, and they end up congesting the system anyway. Andy?
Yeah, so have you looked at any of your methods for like how you could combine like autonomous vehicles with like non-autonomous vehicles, like if you're Uber? And,
Yeah. So that's actually quite an interesting problem. One of the things that I did study that I didn't talk about here is this concept of mobility on demand, where we're doing human rebalancing. And now this is not exactly the same as what you're talking about, but certainly this is a great interest for the future. Yeah, I guess Uber might have to have this in-between phase where they have both autonomous and not. Well, actually for Uber, because all of their vehicles have drivers in them, right, it's essentially, it's almost the same, right? Having a taxi service with some with drivers, some with autonomous vehicles. If you can force the taxi drivers to go exactly where you want them to, then you would have the exact same problem, right? But if you can't, then maybe you can introduce some kind of penalties for not following the orders of the central operator, right? And that's also something interesting that we could study. Tim.
I'm a little bit late, I may have covered it, but in terms of congestion technology growing, did you look at sharing at all? Because 50% of rides in the SF at Manhattan are line, and obviously
Yeah. Yeah. You're right. We have not looked at ride sharing yet. Indeed, that's very much interesting to look at in the future. There's actually quite a bit of literature separately on algorithms for carpooling and ride sharing services, and it's something I'd love to look into in the future as well.
When you do go to do that, you have to model it. If you have an autonomous service that isn't a conventional automobile architecture, 3 people sitting in the back, 2 might have to get out, or 1 to get out. It's very efficient with a new architecture where any one person can get out and the other can get out faster.
Yep. Thank you. Yes.
So it sounds like with the Jackson model, you use the exponential transition distribution. How much does that depart from the real world, and how would that affect actual?
Yeah, that's a good question. So in simulation, we didn't. In simulation, we used kind of a deterministic travel time. We didn't see much departure from the actual model using exponential travel times. But what we can do in the future is actually there's an extension to the Jackson network models called BCMP networks, and this allows you to have more varied distributions on the infinite server queues. So you can actually have what's called a Coxian distribution, which is you can use to approximate many distributions. So that's certainly an area that's worth investigating. Edward.
So
Can you speak louder, please?
Sorry. So between the naive model and the traffic-aware model, so we had so many less cars rebalancing, and yet the quality of service is almost the same. It seems a bit too big.
Yeah. So.
All the rebalancing vehicles are stuck in traffic. That's what I
Yeah, pretty much. They all got stuck in traffic, and one of the caveats here I must mention is that we are using quite a simple delay model, right? It's called the BPR model. It was developed in the 60s. And so this basically says for any road, the more vehicles you have on it, the more the travel times increase. So is it a realistic representation of real traffic? Probably not very high fidelity. It would be great to use a high fidelity, like a microscopic traffic simulator to further validate these results. But also what happens is for the case when you don't rebalance, right, the congestion aware case, what you can say is, well, I'm not going to send a vehicle to you right now because there's too much traffic on the road. Why don't you wait for 15 minutes and then we can send a vehicle to you then, and then perhaps the overall travel service time would be around the same because there's less traffic. And it's a question of do people prefer waiting in their office, perhaps being able to do some stuff and having an accurate travel time ETA of the vehicle arriving, or do they want to just sit in traffic? Right. So there's a trade-off, and it'd be really interesting to investigate this. David.
Is the traffic that you're talking about just traffic caused by your vehicles, or is it built on top of a model of the traffic of the city itself?
This is traffic caused by our own vehicles. So obviously there are other traffic on the roads, and we kind of scaled the road capacities so that our vehicles would be able to saturate some of the roads. And indeed, having extra traffic on the road is an additional unknown, right, that you have to take into account. So it'd be interesting to see how the congestion-aware algorithm would do when we put more traffic on it. Yes?
Have you looked at the trajectories the vehicles
Mm-hmm.
cover in your simulations? How do they differ from the shortest path? Which detours do you have to take?
So are you talking about for the passenger vehicles or rebalancing vehicles?
For the total mileage covered.
So for the passenger vehicles, they'll each route themselves according to, at the start of their trip, what is the shortest time to get to their destination. The rebalancing routes are actually computed, using that optimization algorithm, and then it gives us basically a list of flows for each road segment, and then we can decompose those into paths. And I think for some instances, in like borderline cases, we are seeing that vehicles will take a slightly longer path to rebalance. because of traffic.
So it's unlikely that they will take a big detour just to save
It's,
time.
yeah, because we are minimizing kind of the time that all the rebalancing vehicles spend on the road. So that's something that we are taking into account. But depending on, like, you can weigh the cost, right? So one of the things you could do is perhaps allow a little bit of congestion, right? And then calculate whether or not it makes sense for you to travel on the shortest route while increasing a little bit of congestion, or travel along a longer route and perhaps taking a longer time to get there, right? So, and this is actually something that we recently published a paper on with Federico. Yep.
You mentioned that it was an art or talk, but I'm curious if anyone can possibly how does the problem change when you have constraints in the chart?
Right, yeah, that's, it gets quite complicated actually, because the initial model that we studied with the model predictive control framework considers just routing an autonomous mobility on-demand system, very similar to what I showed. But in addition, it considers what happens when a vehicle doesn't have enough range to get to its destination. So in this case, the system actually becomes much more complicated, because now each vehicle is different, right? Each vehicle has its own charged battery level, and we have to consider them all separately. So this increases the size of the problem, and it's harder to have it scale. But another problem is that in this case, what we're trying to do is optimize until some point into the future, right? And then in a model predictive control framework, what we do is execute that first action and then repeat, optimize, sometime into the future. And of course, during this time, the demand level in the city could change. And if we don't optimize far enough into the future, so the idea is, if we do optimize farther in the future, then we can see the demand fluctuations, and we can do things like opportunistic charging, like, oh, let's charge now and then, in anticipation of future demand. But if we don't do that, and it's pretty hard to actually get to a time horizon where we can, see these large-scale effects, then you don't see that kind of behavior. So there's still some work to be done definitely on this aspect. Yeah.
What was your bidding strategy for the New York data? Like, how many data points did you have for your time?
Yeah. So we took data from 1 day of New York City taxi data, and there was over 500,000 trips. We limited them to Manhattan, so there was 440,000 trips, and then basically plotted all the trip origins and destinations and did k-means on them and clustered them into 100 stations. And that's, yeah. Todd?
So first, I don't know if you were as impressed as I was, but I was impressed that the New York taxi unions were within 30% of the optimized value of the number of taxis. But second, you mentioned at the very end that you're going to need, eventually you'll end up studying these decentralized algorithms. Are those going to be necessary for this to be feasible in real life, or is the optimization problem quick enough that you can already wrap it in this model predictive control and it's fast enough to work in real time?
Yeah, so I think there's kind of two different problems here. The first is, will a centralized architecture work for large systems? And I think the answer is yes. We have shown it, but the problem here is that it could be not so robust to like single points of failure and things like that. So what you might want to do is have a distributed cooperative kind of routing strategy. What can happen then is perhaps the decentralized architecture probably will not have as high of a performance as the centralized architecture who knows everything, right? But sorry, I forgot the second part of your question.
That was it. So basically, solving this centralized problem, is it already pretty fast, or do you worry about the performance of this
so
right now?
Yeah, so for the results that I showed, it's very fast. If you want to take into account extra constraints like not congestion, but charging constraints, perhaps parking constraints, then you might have to solve local problems at a local scale, and then kind of do a hierarchical approach and use some kind of more macroscopic model to do the citywide scale. So that's also a potential research direction, actually. All right, thank you.